All right, in this video, I'm going to talk about the solutions to Euler equations, which are also sometimes called Cauchy-Euler equations. So they are the differential equations that take the form x squared y double prime plus alpha x y prime plus beta y equals 0, where alpha and beta are real numbers. All right, let's start by taking a look at what the singular points of this differential equation are. So we will divide both sides by x squared, the coefficient of y double prime. So we get alpha x over x squared, which is just alpha over x, y prime plus beta over x squared, y equals 0. Okay, so we can see that x equals 0 is a singular point because alpha over x and beta over x squared are undefined there. Okay, so since x equals 0 is a singular point, I know that we do not have a power series solution centered at 0. Okay, but let's check to see whether or not x equals 0 is a regular singular point, because regular singular points are the next easiest thing to deal with. So as a reminder, what we have to do is we have to check the limit as x goes to 0 of x times the coefficient of y prime, so alpha over x. So that's going to be equal to the limit as x goes to 0 of just alpha, which is equal to alpha. Okay, so more importantly, that limit exists. All right, then we take a look at the limit as x goes to 0 of x squared times the coefficient of y. So that's beta over x squared. And this is equal to the limit as x goes to 0 of beta, which is just equal to beta. Okay, so these two right here tell us that x equals 0 is a regular singular point. All right, so the bigger thing here is that since x equals 0 is a singular point, if you actually tried to use the regular series method to find a solution centered at 0, then you're just going to get y equals 0. Okay, so that method doesn't work. So we have to take a different approach. All right, let me illustrate this approach through a specific example. Okay. Okay, so you can see that this is an Euler equation with alpha equal to 3/2 and beta equal to -1/2. All right, so the idea behind this, and therefore it's going to sort of prompt the motivation for the Frobenius method, is to look for a solution of the form y equals x to the r, where r is any power whatsoever. Okay, so in power series solutions, r will be 0, 1, 2, 3, etc., etc. So the idea behind this is that we know those won't give us solutions. Okay, go ahead and try it on this one, and you'll see that you simply get y equals 0, which is indeed a solution, but that's not going to be the general solution. So again, the idea is to say, all right, it seems feasible because these coefficients are x squared and x are just constant. It seems feasible that some power of x would satisfy this differential equation. Okay, so we'll go ahead and find the second derivative of x to the r and the first derivative of x to the r. So go ahead and press pause and do that again. So r is some constant. Okay, so y prime is r x to the r minus 1, and y double prime is r times r minus 1 x to the r minus 2. So we'll take these two derivatives, plug them into the differential equation, and see what should be true about r to get a solution out of it. Okay, so we have x squared y double prime. So x squared r minus 1, x to the r minus 2, then 3/2 x y prime, so plus 3/2 x times that y prime, minus 1/2 y. So we can go ahead and clean this up a little bit. So here we have x squared times x to the r minus 2. So then we combine exponents, we get r minus 2 plus 2, so that's x to the r. Here we have r minus 1 plus that power of 1, so that's x to the r as well. All right, so go ahead and clean that up in the next line. Press pause and do that. All right, so in the end, you should get r times r minus 1 plus 3/2 r minus 1/2 times x to the power of r. Okay, so again, that came from plugging x to the r into the left side of this differential equation. So that means that x to the r will be a solution if that quantity is 0. Okay, so this quantity here should be equal to 0. So what that means is that this whole piece here should equal 0. Okay, why don't you press pause and figure out which value or values of r make this quantity equal to 0. Okay, again, the only way that this times x to the r can identically be 0 is if this is equal to 0. All right, so if you just distribute the r, you get r squared minus r, then plus the 3/2 r minus 1/2, which is here. So then clean this up, r squared plus 1/2 r minus 1/2 is 0. If we multiply both sides by 2, we get 2r squared plus r minus 1 is 0. And that's really easy to factor, as 2r minus 1 times r plus 1 is equal to 0. So we see that this is going to be equal to true. This is going to be true, okay, which means x to the r will be a solution if r is equal to 1/2 or r is equal to -1. Okay? So what we have is then x to the 1/2 and x to the -1. So because it's x to the 1/2, we know that x has to be bigger than 0. So here x must be bigger than 0. So these two are clearly linearly independent, and I know I expect two linearly independent solutions in my general solution. So the general solution, similar to the constant coefficient case, is you take one constant multiple of one of your independent solutions plus a constant multiple of your other one. Okay, so x is bigger than 0. So this is our general solution right here, and I'll leave you to check that y equals c1 absolute value of x to the 1/2 plus c2 absolute value of x to the -1 is going to be the solution if x is negative. Okay, so because of the singularity at 0, I know I'll have a solution in intervals that do not contain 0. Okay, so again, this is the general solution if x is bigger than 0. Simply take each x and replace it with absolute values if you want the solution for x less than 0. And you can check that this is true simply by plugging it into the differential equation. All right, let me give you the general results here in a second. So we get them the same way, I should say, using the same idea as how we got the general solutions for the constant coefficient case a while back. Okay, so I'm going to talk about the general solution of x squared y double prime plus alpha x y prime plus beta y equals 0, where alpha and beta are real numbers. Okay, so we do have to do the same thing every time, which was, we assume a solution of the form x to the r, we find its derivatives, and plug them into the differential equation. So every time you do that, you're going to end up with this quadratic being equal to 0. Okay, and the general solution is going to come from the zeros of that quadratic. Okay, so in the general case, if you plug your derivatives into the differential equation, then the quadratic you're going to end up with is r squared plus alpha minus 1 times r plus beta equal to 0. Okay, so we're going to suppose that r1 and r2 are the two zeros of those. We're also going to suppose that we're just looking for the solution for x is bigger than 0. Then, as in the above, if you want the solution for x is less than 0, you just take each x and replace it with absolute value of x. And I'll include that little tidbit down at the bottom. All right, so if r1 and r2 are the same, then the general solution for the Euler equation will be c1 plus c2 times the natural log of x times x to the r1. Okay, r1 is the same as r2, so obviously it doesn't matter which one you put there. Okay, if r1 and r2 are distinct and real, then, as in the example I showed above, then the general solution will be c1 x to the r1 plus c2 x to the r2. Okay, finally, if r1 and r2 are non-real complex zeros, then they're going to take the form of lambda plus or minus mu I. in that case, the general solution will be x to the lambda on the outside, parentheses, c1 cosine of parentheses mu natural log of x plus c2 times the sine of mu natural log of x. Okay, so we're going to derive this case here and this case here in class. All right, so now let's just do an example of each of the two types that we haven't seen yet. Okay, we don't have to check for singularity anymore. We already dealt with that from the general case. Okay, we already dealt with that from the general case. So we can just, basically, we just have to find out what these two zeros are. All right, let's find the general solution of this Euler equation right here. So we have now alpha is equal to 5. And beta is equal to 4. Okay, so remember the quadratic that we have to solve. R squared plus alpha minus 1 times r plus your beta. Okay, so that will equal 0. All right, so we need to factor this. So that becomes r plus 2 quantity squared equals 0. So we see that in this case, r1 equals r2 equals -2. Okay, why don't you press pause while you write down the general solution. All right, using this first one here, so we see that c1 plus c2 natural log of x times x to the 0 there. And that's for x bigger than 0. Okay, so we get y is equal to c1 plus c2 natural log of x times x to the -2 if x is bigger than 0. And then if you want the solution for x less than 0, as I mentioned, put absolute values around the x's. Okay? All right, I'll give you one more example. All right, why don't you press pause and try to find the general solution of this Euler equation. Okay, so in this case, alpha is 1 and beta is also 1. All right, so you should have found that r should be equal to I or -I. And then you substitute those into this right here. Okay, so we have 0 plus or minus 1i. So I'll write that out for you. So 0 plus or minus 1i, which means lambda is 0 and mu is 1. Okay, so if lambda is 0 and mu is 1, then this is going to be x to the 0, which is 1, and then cosine of natural log of x, sine of natural log of x. Okay, so we'll get y is equal to c1 cosine natural log of x plus c2 sine natural log of x, where x is bigger than 0. Okay, so those are the three different types of solutions for the Euler equations. So in the next lesson, I'll expand on this to more difficult types of second order linear differential equations where the coefficients are not constants, because that's already been done, and they may be a little bit more complicated than these. Okay, so a nice example to as a sort of starting off point for a bigger class of solutions.